Hello, I'm Samrat Ganguly from NEC, and I'm going to talk about some of the things that we are doing to bridge the gaps that we need to support the NFV deployment. And I'm sure that many people are now talking about the application of the OpenStack and the cloud in the telco and the carrier side, where there is a big transformation going on, where they are trying to virtualize the network functions like core or the CPE and routers and the load balancers into a virtualized network or virtualized platform. And that's pushing up a lot of requirements on the virtual infrastructure manager, for example, in the OpenStack. And we are going to talk about like what are some of those gaps, not necessarily a whole extensive list, and what are we going to do in terms of closing those gaps. So a little bit giving a idea of what are the key properties that are like important in most of the complex NFV deployments, and we want to focus on little complex or little more, I would say, mission critical type of applications, like for example the virtualized evolved packet core, which is the mobile core that drives all the data traffic from all the mobile applications, or for example the virtual CPE that is about virtualizing all the home premise equipment into the cloud. So these are like very complex applications, and these are not probably like smaller application, let's say like a DNS or a DHCP that you can just virtualize, take the application from the box and put it in as a VM in a virtualized environment. It doesn't work. So in these complex applications, what you're first trying to do is that you're trying to unbundle this whole application into different pieces and roles, and they work as a scalable distributed system and with different roles. And what happens is that when you try to unbundle this application into smaller different VMs, they all have different type of requirements, and it's not like one particular resource framework that fits them. So what are those different requirements? They can be like, each of these different parts of that whole application may have different type of CPU core or memory requirement. For example, in case of a virtual EPC, if you unbundle them and break them into, let's say, a control plane processing unit as opposed to a data plane, then the control plane might have more CPU requirement, while the data plane might have a more of an I/O requirement coming up from the compute host. And there can be also different type of networking requirements. So the question is that you have to create an environment that can actually sort of tune and specifically support different type of requirements as imposed by those functions. The third important part of any of this NFV deployment is creating a predictable environment. So you can't think of them as like web applications running on shared infrastructure, and the idea is that how much you can push applications and make your resource better utilized. Here it is all about the predictability. When you're trying to actually support like packets going through the whole platform, you have to ensure that there are like real SLAs there. There are like packet level guarantees, delays and jitters has to be under a bound, and those type of predictable environment is an important part of such a infrastructure. And then the next part is, of course, about the reliability. There is this whole reliability requirements comes into play here, because you want a system that is always available. You can't have, for example, a service virtualized which is supporting, for example, the voice calls, and it is not available. No consumer would want to have a system that cannot give a service when you're making a call, or even if it leads to dropping the call. So reliability of those services on top of such an environment requires a lot of critical thoughts and also mechanisms to ensure that there's a good amount of availability guaranteed. And most importantly, it's also important when you're talking about resources that the overall packing of all those VMs in your entire data centers, there is some sort of a scale that you're not trying to make a lot of idling cores in the whole system, that even though you took care of a lot of predictability and assurance and other things, but your system is actually requiring a lot of servers. So from there, let's get into some few of the key requirements and some of the gaps and that we discuss here and how we are trying to treat them. So one of the important part is that is about how to place the VM in the compute nodes. So a typical Nova scheduler and other things, there isn't a lot of policies that you can add in terms of how you want to place the nodes. But in a case of let's for example, a NFV deployment, another example case illustration of a EPC, you have to think of many things. For example, you have to think of like what's the VNF or the virtual machine size requirement. There might be a VM which requires, let's say, 6 cores, while other may require, let's say, 2 cores. So you have to find out, let's say, that what's the physical machine which has support of those availability of those cores, and then based on getting such a topology information from each of the hosts, you have to make a decision that where that VM can fit in. The second can be based on like different traffic profiles, or there can be even policies like, for example, you need an active and standby nodes to be in a different location, not in the same host, or there can be also issues related to what's the traffic between them. So what you need is a more sophisticated resource allocator which is able to get information and then try to place the VMs in the right physical host, and that leads to a more predictable performance along with high resource utilization. In order to support this type of things, you need more information that you are able to get right now from the OpenStack, for example, the ceilometer, which only provides you information related to the guest VM. So the part what you need is 2 type of information. For example, the NUMA topology for any of the physical hosts, as well as network interfaces, because these are 2 important resource information that you are able to get about a typical physical host. And also you need to get maybe more information out of the Nova, let's say adding the available CPU memory and the device information. So in order to make that type of a decision, you need a resource allocator, and that is what we have added on top of the OpenStack, which actually has a whole database state about all the CPU memory, device ability, and the NUMA topology across the entire infrastructure, and then uses that to basically use the Nova to place the VM into the correct physical machine. The second thing is that there is a need for more flexible configuration. It can't be as simple as that, okay, I launch that VM and it gets connected to my OVS and be done of it. There is, like we were discussing, there is different VM might need different type of core or type of CPU affinity rules, and those CPU affinity rules are actually defined by your current availability and the NUMA topology. Also, for the networking standpoint, you also need different type of supports. For example, your vNICs from the VM might be connecting to a pass-through type of interface, or an SRIOV, or a simple generic OVS, or maybe an OVS DPDK, where you want better I/O performance. The question is that in a typical scenario, how can you go and flexibly map these type of configuration to each of the VM when they are getting booted into the physical machines? So here's our current approach of doing that. What we are doing is, again, that same resource allocator, which is able to get all the information and finds out that, okay, for this particular VM, before it boots up, we need to apply a set of this configuration. So that same agent which is sitting in the compute node actually gets the libvirt.xml from that resource allocator, which actually defines all the configuration that are being assigned for that particular VM. Now, we have added a plugin into the Nova that before it actually boots up, that uses the target libvirt.xml from that agent before the VMs get booted. In that way, what happens is that we are able to apply a specific configuration for a given VM. For example, a typical case can be, for example, there is a data processing VM which needs a DPDK support because there is a lot of I/O activity going on. So it needs to use an OVS DPDK, or maybe it wants to use a pass-through or a SIOV interface. But there might be a management-related VM which may not need such a information. For that, we can use a normal OVS. The third part is the inter-VM networking, and that's sort of using more than what is available from the OVS. So we have supported our neutron agent plugin that supports VXLAN along with the VLANs. because you need to have a overlay support in a typical data center environment. But more importantly, it also allows you to use multiple NICs so that you can create reliable inter-VM networking out of that. And the last part of the support that we have added is to create a lot of hardware level information back to the system so that you can actually have a auto healing mechanism that's not just about the VM availability, but also in terms of your like disk, memory, CPU, NICs, and all those availabilities are tracked and traced, and that can be used for your orchestration system to support higher level availability. So with that, actually, we wanted to share some of the things that we have added. So we are working right now with the partners and the distributors to make some of these additions into the upstream, and hoping that over time that OpenStack will bring these things as a part of their distribution and their thing. So that sort of concludes my talk in terms of what are the requirements for a typical NFV deployment, and really thank you for listening to this talk. And if for any questions, please contact me in the NEC.